So again, I wish you again good evening. So this is our first tutorial session on NPTEL online course on mechanism and robot kinematics. So again, just to iterate, I'm Krishna. I'm doing my PhD in fourth year. My research topic broadly covers magnetism and elasticity. So during this process, I have been interested in robotics since my work has applications in soft robotics. So yeah, so as for today's class, I would it's more of a dot clearing session. That's what the official it's called. So although we'll try to go beyond what is being covered in the course in the official lectures. So that's the first part of what we plan to discuss today, which is how do we organize these sessions, which is going to be of at least 20 hours. And then will be just reviewing some of the fundamental ideas which was discussed in week one, and then we will um, solve some simple problems. I think that will be quite a bit here today. So we'll be reviewing introduction. I'll just be following whatever the topics broadly was taught in the week one of this course. And then we will solve some simple problems. Maybe some of them may be repeated version of what was discussed in the class. So please don't mind about that. And then so that is the plan for today. So as for organization part, so what I and here I mean, please all of you, I very much encourage you to please give suggestions so that we can plan accordingly. And especially, I think Deepak, since you have experience in robotics, so I think that would be very nice to discuss here. How should we plan it? So
Yes,
what?
yes.
Yeah, sure. So what I right now I'm planning is that we will first will in every lecture we will be reviewing whatever was discussed in the classes. So that is always there. So review of materials, lecture materials during the classes for the corresponding week. So that is always going to be there. And we would be solving some problems as well, maybe from assignments. Yeah, and even we'll repeat whatever the problems that were solved during the class. Since we don't clearly know which book the professor is officially full, I mean, he's following. So I think that's the way we have to do. Otherwise, there is a book called Modern Robotics, which I have been reading. It's so we can we it would be nice if we could even I'll share it with the soft copy through this channel. And I think that would be something like an uh, additional book that we shall read, or some of the what you call topics we shall just peruse from there. And second part, like the plan is to even digress from the official lecture series, or as per the course, from the, so to speak, the NPTEL classes. Uh, so one thing that I have in mind is that we will be learning and doing some simulations using MATLAB. So I think that should be one particular area, learning and maybe implementing some algorithms. Since I am also learning simultaneously, so we'll do it together. Uh, although I'm good, I mean, so excellent, but at least I have an intermediate, what do you call? So that's one thing that we'll do. We'll try to use software tools, MATLAB, even Python, but I think MATLAB would be it's at least more doable, for such a short course. And then we will be, what I'm playing right now is that we can, there is a software called Capella. So I hope I'm just I'm what is the so the software is called Coppelia Simulator. So it is an open source software for robotic manipulators. We can implement algorithms and learn about what we call as the path planning. I think that's what we later learn during this course as well, and do some say simple experiments in Coppelia simulator. I'll send the link also about this software. And the third is there is yeah, some of whom you will have time, then there is a course on Coursera, which I am doing as well. So the course is called Modern Robotics. It's offered by, I believe, let me just check so that because there are two courses on. So I'll just confirm which one is it. Is it Modern Robotics? Okay. So, mm, yeah, okay. So it's by University of. Okay, I'm just checking. Mm, I think it is Northwestern University, I believe. Yeah. So this book which I'll be following, and I'll definitely I'll share it everything on this channel that we have set up for these tutorial sessions. So that's what we'll be doing by Northwestern University. So this is I mean yeah, please Deepak, do you have any suggestions? Like these are just some of that things that I have in mind as of now.
Yes, it's very nice, Krishna. These are very effective tools as well as books, which will be
Yeah, yeah.
helpful.
Yeah, the thing is because say it would be better since this is independent of the official NPTEL system, right? So I'm more of an external TA. So we have full flexibility to decide how we conduct the tutorial sessions, what we discuss. So it's like it depends on us how we want it to be. So so it should be beneficial for all of us. We shall learn more extra things apart from what was discussed during the because the professor, I think he makes his best efforts to make things very comprehensible. So why not we explore further uh, during this program? So so this was the overall, and then we'll keep on making adjustments. And although the thing is the course is also not very long, it's I think, and this tutorial sessions would be of 20 hours. So we'll try to make the best use of the time that we have. So now I'll just start with some of the introduction part, what was discussed during the. So at first we start with kinematics. So kinematics is like there are two parts of this particle mechanics, right? Two aspects. So one we call as kinematics, and there is kinetics. So kinematics is say you have some particle, and then say some force is acting over this particle, some force, some F vector. Because of which this particle of mass m will have some motion. See if it's force is acting, if the force is continuously acting, then definitely it will accelerate because that's how it works. Some with some acceleration vector, and if the force is removed after some time, then as per Newton's first law, things will keep on moving with a constant velocity in this case. And so from Newton's second law of motion, we have the relation between force and acceleration like this. Now, so this is the proper dynamics of any mass particle, so to speak. So what we do is we separate it into two components: force and its nature of forces, and force itself and application. This part comes under kinetics, because the thing is it's very involved, like how forces are generated, how it's being applied, from where it comes. So that part we don't want to worry about. So the other part is what we call as kinematics. So it's like a complement to it. So kinematics only deals with what will happen to a body, just how it's displacing in a sense. Like, given a force, say force, we know it's just we don't want to know about the cause, that how does the force apply. We say that okay, we have the force, how will the body move, which trajectory it will take. Say, since we live in 3D space, and the most useful coordinate system is always the standard Cartesian coordinate system, which is denoted by XYZ, which is a right-handed coordinate system. So what we see is how will the, say, particle move in this particular frame. So that is what essentially. So that is what essentially what we do in kinematics. So kinematics is what. So in kinematics, what happens is we require three variables. We start with, of course, the first thing that we see is acceleration, provided mass is acting. If force is acting, then because of acceleration, obviously velocity will be influenced, isn't it? So velocity will be affected, and velocity, again, what does it create? Like, the body will move, so there is something called displacement. And the thing is, we apply force, acceleration is generated on the body, or the body accelerates, acceleration leads to change in velocity, velocity leads to change in displacement. That is the actual order. However, by virtue of how they are mathematically linked, so from the mathematical perspective, we start with displacement first. So say we have some r vector. So this body is located at some r vector here, this particular point mass. Now, this point mass will be a function, the motion will be a function of time, of course, and it's a vector quantity, which means that it will have three components: x as a function of time, y as a function of time, and z as a function of time. So this is essentially what we call displacement. And you know very well the difference between displacement and distance. So displacement only cares about the final and initial points. It does not worry about which path the body took. So if, say, we have started from here and ended at here, it started at time t0 and ended at time t1, it does not care about which path we took. So the displacement is just the Poisson vector at t1 minus Poisson vector at t0. So that is the displacement. Now then, velocity, how we define? So velocity is essentially the derivative, the time derivative of the displacement vector. So that gives us velocity. Likewise, acceleration is we move one step forward and carry out a second derivative operation, and this is equal to dv vector by dt, which essentially is the second derivative of the displacement vector. So this is what we do with kinematics. And so next what we do is, now we'll talk about something called mechanisms. So mechanism is essentially it's nothing. It's essentially just say connection between different rigid bodies. So they are connected in some manner. So say these are this rigid body one, body two, body three, body four, body five. So their connections create something called as a mechanism. So that is what is the base meaning of a mechanism. So it's just essentially just connected. It's a connected set of rigid bodies which may have some purpose. Depends on what our purpose is. Like based on that, we'll have different sorts of mechanisms. And so you'll always typically see that in general, mechanism can be of any, I mean, the rigid bodies can be of any shape. Any shape depends on the operations. But we'll later learn during the kinematic diagram that you prefer to represent one rigid body just by a simple line. And that we'll come to know later. Why do we do so? The thing is, it's easy to form the a diagram, and then we can compute all those quantities that Deepak was talking about, like the computing degrees of freedom and determining based on the degrees of freedom of each individual, say, joint, how it restrains the connection, the interconnected set of rigid bodies to not being able to move in certain way, maybe translation or either rotation. So that's what we'll discuss later. So the idea is just that we want to have this set of rigid bodies in such a way that the bodies move within this connected set with some relative motion. So that say if this body is there and we by some mechanism, by some say actuation we call it. So actuation uh, is a way of applying force to one or more rigid bodies within this interconnected set. So say by virtue of certain actuation, it will deform like this. So now I became something like this, say, by virtue of some. So this is essentially what you see is there is the before this body with, I mean, body number 5 with respect to body 1, it was, say, if you draw a just line, just some very vague, I mean, just I'm trying to give a very simplistic view here. So this body was lying on the left side of this particular dotted line. By virtue of actuation, now it shifted to the left hand side of this particle of this body number 1. And body number 1, mind you that it's still at the same place. So which means that there happened some relative motion between body number 5 and body 1, and the other bodies as well, like body number 2 moved, 3 moved, 4 moved as well. So this relative motion is what we want, and this is what we want. We need, because we want to exploit this motion for our purposes. Say if you are using some sort of a such connected set of rigid bodies to pick up some body, and then we call, okay, it's a robot, isn't it? So that just comes later, but essentially that is the fundamental idea of mechanism and all. So idea is always how do we provide say the force to a rigid body, and how does it deform, so to speak, how does it uh, change its relative motion with respect to the to others, I mean to the other bodies, and that will help us in getting some new properties, new functionality, so to speak. Okay, so what we'll do is, yeah. So now let's move further. So this all the slides will be available, but again, I am just messing everything up. So it is still, yeah, we can always discuss if there is something we could not figure out ourselves together. Okay, so okay, so we move one step forward now, and we talked about motion, we talked about displacement, we talked about force transmission. Then we also have ultimately the aim of using this mechanism is it will be used in essentially mechanizing things and automating. So that is the automating some process. And I'm not talking about some say software process, it's some hardware process. So I'll just write it down. Some hardware process which involves physical movement of things. So that is the main a goal of this mechanization. So I mean goal of this mechanism. So now processes can be several. It will be in say in if we can have some sort of a welding arrangement which can be automated. Then say packaging. So in large factories where products need to be packaged in various ways, then it's not possible, say, if the throughput of that manufacturing unit is quite high, then it may not be possible to do individually by, say, say, by humans or by those employees. So we may want to automate the entire process. And if say the machine just churns out some products at faster rate, then we will not be able to do it with great efficiency if we do manually. So that is the place where we use mechanisms. And even in manufacturing, assembling, and all that, there are myriad of what do you call applications here. And in healthcare, so gradually in recent years, with the rise of what we call as soft robotics, then we also have uses in doing surgical operations. And essentially, they are very deep surgical operations. Say we can guide certain. These robots are also called some catheters. We can guide using some magnetic field to the location where the surgery, or even say we want to perform, or we want to say just able to visualize that affected area. So that is where we can have all this. So that is essentially one of the goals here. And now, why do we need to study the about mechanisms? The thing is to synthesize any such mechanism. We require, we need to have, say, detailed knowledge of kinematics of the mechanism that we want to say assemble, so to speak, right? And we want to have all those tools and techniques beforehand so that we can either prior to design itself, prior to manufacturing itself, we can have the idea, or even say if we can, even after say we have manufactured, then we would like to know, okay, why something failed. And it's always good to have it. Is very indispensable to have such knowledge, right? So that is what is eventually, isn't it? So what we'll do is I'll present some terminology here, which I believe it was not discussed during this process of during the lectures. So say you have some mechanism. I mean, again, I'm using a very crude schematic here. You have some mechanism, and you have certain some say what we call an end effector, we call it. So this is just like a set of rigid bodies connected together. And there is something at the end which is meant for some purpose, right? That's what we have designed this mechanism for. So what we'll do is, so the space in which this particular mechanism can say orient can what you call can exist. Say if you have a robot in 3D space, then that becomes what we call as the configuration space. So configuration space is the space in which the mechanism can, what you call mechanism, it will can say like it will just can say orient in a sense. So if say if we are in 3D, then if we are working in 3D, then obviously the mechanism can take any point in that 3D space. So that is what is configuration space. And if we have say what we call uh, planner, then our mechanism will be the configuration space will be in 2D. So that is one thing. The second thing is what we call as the to what we would like the mechanism to be working on. So what is the effective function of that? So that will be decided by this end effector. So we say we want to design some mechanism, say to pick up some body, something from a table. So this is some say table we have, right? So what we are doing is we are picking up some body from here and placing a different point. So that means that, and it should be only on the table itself. Then this becomes what is called as the task space. So task space will be only this the surface of the table. So that's how, and mind you that this configuration space and task space are usually independent of each other. So it's just that for any task, what should be the configuration that we want the mechanism to have. So that is essentially the goal here. Fine. And now we'll move to discussing more about the some other nomenclature as per the notes here, as per the lectures. So we'll talk about what is a kinematic chain. So I hope you know what is a rigid body, right? Uh, could any of you please say? Hello. Uh, am I still audible or
Hello.
like, yeah, yeah. So could any I hope we know the meaning of the say what we mean by rigid body, right? So how would you define a rigid body? Because ultimately it involves the meaning of rigid body, isn't it? So how do you define rigid body? So could any of you just please explain, just give a brief description of a rigid body.
Rigid
Yeah.
body is a body which is non-deformable.
Huh, 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 huh. Yeah, that's true. So it's like a body which, even if you apply forces, doesn't matter. It won't deform in the sense that there won't be any relative change in the positions of, say, any two particles within the body. However, it can still translate, means it can move along X, Y, Z coordinates, and it can also rotate about any axis. So that is what essentially rigid body is. So yeah, so that was what rigid body is. And in this robot in the robot in the as per the scope of this course, we would only be dealing with rigid bodies. However, in soft robotics, the material tends to deform as well. So it's a different area altogether, right? So that's why we start with in rigid body with rigid bodies, we can have a chain. Again, it's just I'm just iterating again. Some set of connections, some sort of rigid bodies which are connected. So if the rigid bodies are independent, then it does not make sense. We cannot make any use of it, any particular use of it. It's only when they are connected, then we can, it has a part, it can be made to serve some purpose. So these are all individual rigid bodies. And you have these connections here to connect two individual or two or more rigid bodies, right? So these rigid bodies are also called links, right? And connections, as we will find out later, are also called as joint. So essentially, the entire field of robotics is, and any say this mechanism or any such thing, right? It's always just composed of two things, joint and links. Just using this two, we can have several varieties of infinite possibilities of mechanisms and robots for different purposes. And as we discussed previously, planar case or planar kinematic chain is when all links move in. So all links will only move in one plane. So if it is XY, then it will only exist. The deformation, sorry, not the, yeah, this motion will only take place within XY plane. So that is what is called as planar chain. Now, an example is, say you have, you look at the door, but from the top. Or why go so far? So say we have, just as an example, right? Say you have some nut. You have a nut. I'm sure it's a hexagon. So, and then use some wrench to open it. Now what happens is, now temporarily, this is also some sort of a mechanism, isn't it? Mechanism where this nut is fixed. It can be considered to be some ground. And there we are using this wrench and rotating it. So this wrench is able to rotate in this axis anywhere in XY plane. And and only when we take it out, then only, but when till it's connected to nut, to the bolt, we can only say rotate in XY plane. So that is an example of a planar chain, and it's a very simple chain with just one member. And there are two what you call planar chain sessions. Two rigid bodies here, but one of them is just, so to speak, right now we'll just say that okay, it's a joint, it's a connection here, because this can only rotate about its axis, and the wrench is the one which is affecting that motion. So we are actuating the wrench, and actuation is because of our effort, because we are using our muscle energy, muscle force to rotate this, and then we are able to say rotate this nut, isn't it? Now, then we have something called as a space kinematic chain or spatial kinematic chain. So spatial kinematic chain, what happens is, it is a mechanism which can move in 3D. So the motion will be in 3D. So it's like, um, you say something like, say you have a ball and socket joint, right? You take something and you have some ball and socket joint, and then this part. So we can rotate it the way we want in 3D space, any way possible in 3D space. So that is an example of spatial kinematic chain. So there are two links here. So this is link 1, and this is link 2, and this is the connection. So this is a simple example of what we can call a spatial kinematic chain. Now there is a classification for link as well. Link classification. So this is a very simple definition here. Let's say you have a link and it's just connected to one side. So say it's connected to another link, and this side there is no connection, so to speak. There is nothing on this side. So, and this link we here say is this link is connected to say some other link as well. But this link here is only connected on one side, or it's connected just once. So that is why it is called as singular link, because it has just only one connection. Now this connection here has sorry, this link here has two connections, this as well as this. So this links is called binary link. And then we have certain links in more complicated situations where say we have three. This link has three connections, 1, 2, and 3. This link here, this one. So this link we call as a ternary link. Yeah, these are just some definitions which comes in handy later, right? And the connection here between say two rigid bodies is what we call as kinematic pair. And it's very well, what do you call it? It's very obvious from the definition as well. So it's just, it's something which connects two rigid bodies. And that's the reason we call it up. It's essentially a pair. And because we are only dealing with the relative motion, so that uh, we use the word called kinematic here, right? So that is what was here, yeah. So moving further, and yeah, today will be a boring class. From next next time onwards, we'll also have some element of something which keeps us more involved and engaged. Okay, so now we have we need say we have some planar mechanism, just as a simple example, and I'll just be presenting what was discussed in the class as well. So see, this is how you look at the door from the top. So there is a hinge here which connects with the wall, and this is the door. Now, before it was, the door was closed. So it was something like this, and the hinge was here as well. Right? Once you opened it, it took some shape. And from this position, this reference from the closed position, it rotated by some angle theta. Right? And this is the hinge, wall. So this theta is a quantity which gives us the amount of deflection, or how much has the door moved from its closed position. So this theta is also called as pair variable. And you'll see that these are something which in such scenarios, it's very easy to define pair variables. But if you look carefully, there are also degrees of freedom. It's just that in this particular case, it's very obvious. But in many complicated scenarios, we cannot very have a very we cannot very are able to clearly define the pair variable. And it's very much say it's complicated to define a very specific pair variable, right? And now even this pair based on the kinematic pair also has different types, so to speak, as per the lecture here. So the classification of pairs, so it is also of two types. The first type is lower pair, is when there is an area contact between two rigid bodies, or say two links, since we call rigid body as links. So this will be an example when we have this hinge joint. So this is a link here, and there's some kinematic pair, and then we have say another link which can rotate in this manner about this axis here. So what happens is if we look at from the sideways, then that's how it's going to look, isn't it? and there will be something which connects both of them. Say you have some bolt, say double nutted bolt, so to speak. It had both heads on both sides, and then we are able to rotate about this axis, along about the axis of this particular bolt here. Then what you see is this area is under contact, like the faces of this link as well as this link is in contact. So that's why we call it as an area contact, and such types of kinematic pairs are called lower pairs. Then we have what we call higher pairs. So higher pair is when we have line or point contact. In this case, these are some connections between two rigid bodies, which such that say, as per the example in the class, we had that some cylinder rolling over another rigid body. And so the connection is only here. And as it rolls, the line of contact changes. So this part is called, such connections are called as, this here is line contact. There is a line contact between both of them, between these two bodies. And point contact, we have, say, some ball rolling over some floor. Then there is this, it will be connected at just one point. Okay, so we're here. So we had this floor here over which some ball was rolling, and it was connected at just one point. So this is what we call as the point contact, and such kinematic pairs are called higher pairs. Now we'll come to the different types of kinematic pairs. So some of the standard ones we'll look at. So types of kinematic pairs. So first what we have is revolute pair, also called as hinge joint. So as we discussed, we have some rigid body. They have an area contact, and it's connected at this point, and then it's free to move, only rotate about this point, that also in a plane. So here is where answering to Deepak's query. So because, say, this body, say, assume that this body is fixed, this rigid body is fixed. Then what you say is this other rigid body can only rotate in the plane, in the XY plane. So it can only undergo rotation about Z axis. Right? Z will be pointing upwards from the right hand coordinate, this one, coordinate arrangement or right hand rule. So which means the only motion that this body, the body number two, can go with respect to body number one is rotation about this axis, about this hinge axis, or what we call as the revolute pair. So this is a hinge joint. So that this is the only motion possible, and this makes it having 1 degree of freedom. I know it will be somewhat convoluted, so let me start from the beginning. Let's go into the property of a point. I think let's start from the beginning, and then it will make much more sense. Say we have a point mass of some value, mass m, and it exists in X, Y, Z coordinate system, which is the Cartesian space. Now, if you apply some force to this body, it can undergo uh, how many, I mean, along with what all motion can it take? Deepak, let's start with you. Like, what all motion can this body, can this mass take?
Yes, Krishna. It can translate in x direction, y direction,
Yeah,
and
yeah,
z direction, translatory motion, as
yeah,
well as yes, rotational.
yeah. Now there is a catch here. So I'm telling beforehand that it's a point mass,
Oh,
right?
point mass.
Yeah.
Yes,
So okay, so there are three motions possible in X, Y, and Z motion, what you called as translatory motion, right?
yes, right.
Yeah. So translatory motion along three directions, which means that we have 3 degrees of freedom, so to speak. So degrees of freedom, the actually definition follows from classical mechanics. So it has a very complex definition. Just to tell you, it's like, so the degrees of freedom are the minimum,
Yes,
yeah, minimum number of coordinates which can describe the motion of a system of any body. That's what we call degrees of freedom. So the word is minimal coordinate set in classical mechanics. So here what we say is that's why I'm starting from the very basic, that a point mass has three translatory motion translatory I mean three types of translatory motion along X, Y, and Z coordinate system, along the coordinate directions. Now when we talk about rotation, can a point mass undergo rotation? What are your views? Like, can a point mass undergo rotation?
perhaps no. It can only translate thing.
Yeah, the thing is, we cannot visualize rotation of a point because point by
Yes,
definition has zero dimension, right? Isn't it? So point has zero dimension. So point has zero dimension, which means that we cannot define any length of the point. So point has no length, because of which you cannot visualize what you mean by rotation here. There is no, I mean, the question of rotation doesn't arise because by its very virtue that it's just a point which has no dimension. So even if, say, it were rotating in some hypothetical sense, we could never say that it has rotated and we could never measure it, because the thing is, in reality, it cannot, point cannot rotate, because to rotate you need some what you call certain mm, to be able to say measure rotation, you require to view the body at least say 2 points. I mean, from two perspectives. Say, since you say that okay, this body, I was looking here from here, right? Our eye is looking at this body, say some arbitrary body, isn't it? So we are looking at this body, and if it has rotated, say if it has rotated, then it will become some, say, this body. Now we can clearly see that the point which was supposed to be, which was say directly in front of our eyes, now has slightly shifted from our side of vision, or from the line of vision. So we say that, okay, this body has undergone some rotation. But again, this rotation is not about certain axis. It's just, I'm just giving a very crude, that we say that, okay, this point has rotated because we are able to see that it was before here and now it is at here. So we say now what we do is, just to make it clear, we keep this body on a table and rotated it. And I had drawn one line here and put this body in this configuration, marked this point, rotated it. Now we can clearly see that there is certain deviation from this point of this point here, on the condition that one point is fixed, some position of this body is fixed. Then we are able to measure some theta of the rotation. But for point has no dimension. So no dimension means Unlike in this case, where we could see that okay, it has some length L from any side, isn't it? So we could make a sense that okay, it has rotated because this is still the length L. And now what we'll do is, now if we look from this side, okay, I think I'm making things very complex. So let me just have this. So this was the length before rotation, and this is the length, and this length is still the same. This one is L, this one is still L because rigid body, so no internal deformation. However, when we look from the side on the of the same body on the table, we see that the projection here has, so it was say let's call it L only, but this is some L prime, and we see that L prime is less than L. So we were able to figure out in using a very crude way that it has undergo rotation. Now let's do the same thing for this point. You arrange it the same way, you rotate it, you have L, and again you will what you call rotate it, isn't it? And mind you that I'm not taking special cells because the counter question is, but then how can we find the rotation of a cylinder? So we are not talking about space. This is for a very, this is for a just, I'm looking at a point, right? Now this line is already zero. I mean, the length of this point is already zero. No matter when you rotate it, this length cannot be measured. It's still zero. And there is no marker on this which can help you decide whether it has rotated or not. So that is the reason we say that, yeah, it's a very crude of explaining, but that is why we say that a point can only undergo translations, never rotations, because rotations are degenerate. It does not make sense for a point to rotate. So that's the reason to understand the concept of rotation, we require at least 2 points. So say we have XYZ coordinate system. Now we say it's some imaginary line connecting both of them, right? And if we are able to move one body with respect to another, keeping this fixed, say this is fixed and this is moved, then this imaginary line connecting both, what we see is there is some change in orientation in this particular coordinate system of X and Y. Although say when we look from at the top, then it was earlier here uh, before we rotated it, and then now it is here. So this is the angle of rotation. So that's the reason to define, to understand rotation, we need at least 2 points. That's the reason why we can say that I'll just have a new page, because here we are moving into I think there is a very sometimes it becomes complicated to understand the ideas of these degrees of freedom. So that's why I'm trying to spend so much of time right now here. And okay, next time on I'll just have some empty pages so we don't face this problem. Okay, so for a rigid body, so this point, these 2 points, when connected with some line, if there is no change in length of this particular line between these points, is the simplest. This is the simplest rigid body. You can never go much beyond this. I mean, below this, like this is the end point of what you consider to be rigid body. You cannot go any further down. So for a rigid body, now let's look at this, what all it can do. This body, and we define some virtual center. Let's say this center. So this is body 1, this is body 2. There's some center of this bodies which is at the midpoint of the, or midpoint or any point. Say if the masses are equal, then it will be at the midpoint. So this will be as if it's one particle. So we can call it as if it's a particle here. Right? From that perspective, we can, that's what we say. So what we can do is the entire mass of these two bodies can be said to be concentrated here. And this is what is also called center of mass. I hope you recall it from class 11 years. So this is what the center of mass. Now center of mass is a point mass. Now you see that as we learned from the party, from how many what do you call how many types of motion it can have, is that it has three translations. Three translations possible. Fine. That was for a particle, because since we are concentrating everything at the point at the center of mass, now it becomes a point. It's a point mass and it has 3 degrees of freedom. Now let's go into the other aspect. So you have these two bodies. So this is like center of mass. I'll just make it double the volume. So double the area so it looks much better or more, say, physically. There is X, Y, and Z. Now what we can do is, let's say that if we were be able to bring this entire body down till Z is equal to 0. So this Z is equal to 0 is the XY plane. Then it would have been as if both the points are lying in XY plane. So say I'll just draw like that. I'll just call it, say, from this perspective, X and Y. So this point mass is here. These two connected mass, X and Y. Now let's define some axis passing through the midpoint of these 2 points and which is parallel to Z axis. So this axis, going back. So this axis here is parallel to Z axis. Now what we can do is we can keep this fixed or just keep the center fixed, like let's not move the center, and then rotate it about this axis in such a way that this point goes here. I'll use a different color. This point goes here and this point comes here. So it's like this goes here, this goes here, and the line is this. So what you are able to say that, okay, if there are two such points which are connected by some line or some, say, link, so to speak, and no, let me keep it simple, connected by some line, then what happens is we can have rotation about Z axis. Okay, so what happens is now we are able to have 3 translation. I'll just call it 3t plus 1r. Now what we do is, fine, since we have so much of freedom with these 2 points which are connected by this line, why cannot we have something like this? Say X, Y, Z again, and consider both these masses to be, say, it was something like this. And now let's just change the orientation. Change the orientation and bring it such that let it travel, and it should be such that eventually when Y is equal to 0, this one lies in Z X plane. So this one will be something like this. This one Y is equal to 0. Now again, using the same logic, let us have an axis which is parallel to Y axis and rotate it such that this body moves here, this body moves here, and this, at the center. So we have this line connecting. We have this line connecting both the points. Now what we are able to say that there is, okay, what we found that there is one more rotation possible about Y axis. So which means one more rotation added. Likewise, one more about x-axis. So you have about y, about z, about y, and about x. So that's the reason you say that a rigid body has three translations plus three rotations. So that's how we are able to. And mind you, as I told, right, 2 points connected by a line is the simplest rigid body. You can never have a more simpler rigid body than this. Like this is the end point of what you call a rigid body. Okay, now let's come to hints, and then we will be able to clearly understand the thing that we are facing with as Deepak was mentioning. So we'll come here, drawing that. Uh, okay, so I'll have this rigid body here, this rigid body as well. This is fixed. Say this is fixed, like we are not allowing it to move. And later we'll come to, they also call it grounded, like the professor will use the word called grounded. So this is what grounded means, that it's not allowed to have any motion. Now, this is a planar. Okay, I think there was something more that I want to discuss here, because then it will make us much more easy to understand this problem. So what I'll do is, we were talking about rigid bodies. So rigid body has 3t plus 3r degrees of freedom. So mind you, we are only dealing right now with degrees of freedom which are visible to us. In general sense, in classical mechanics, we can never beforehand know what is a degree of freedom. It has a very abstract meaning. Okay, so now and this is only when it is in 3D space. Now what we do is, let us bring that body in 2D space. 2D space means x. So what we do is, we had a body in 3D space, some body in 3D space, or maybe we'll take the link itself, those two masses connected in x, y, z. Before it had all the freedom that it could move along x, y, z, and then also we were able to rotate about x, y, and z axis. Now what we do is, we are restricting it, restrict the motion to 2D. Now what happens is, what we do is, when we restrict the motion to 2D, then our entire the configuration space is XY coordinate system or XY plane. So we bring both these points here, which are joined by this line. Now what we can have is, this center of mass is here. So this center of mass can move along this direction, can move along this direction. So which means that there is Y two translations, because that translations is not allowed because we have restricted the motion to 2 dimensions. And one more thing that it can do is, keeping this center of mass fixed, we can rotate. So this can go here and this can go here, with this line being connected to connecting both of them. So which means that there is 1 plus 1r. And now you'll ask, what happened to the other rotations? Can't we do it? The reason is, simple answer is no. Why? Because say if we were to rotate about to x-axis, then one point would go, will have some positive value of z, and the other will have a negative value of z. But the thing is, we are not allowed to move outside of, we are not allowed to move, not allowed to move outside of z is equal to 0. So you see, it places such a big constraint. that if we can never have z is not equal to 0. So which means rotations of x is clearly not possible. Even for y, say if we were about to rotate these 2 points about y-axis, then this point, and following the right hand rule, then this point would go inside, which means that this would have negative z, and this would come outside, which means it would have a positive z. Again, it violates z is equal to 0 condition. So which means that's also not possible. That's the reason a planar body, or rather a planar motion, any body undergoing a rigid body undergoing planar motion has 2 translation, 1 rotation, and that's the reason we have 3 degrees of freedom, 3 DOF. Fine. Now I think with the, and mind you, a rigid body undergoing planar motion is also called as a planar rigid body. That's just a play with words, but that's how it is. It's a planar rigid body. With the background in our hand, now we can move and talk about hinge joint. And now you'll see it is so clear to understand this. In hinge joint, or what we call as the revolute pair, we have fixed one body. This body is fixed. What we see is because of this body being fixed, this connection here, this what we call as the, yeah, it's essentially a pair. This connection will not move. So this joint or this pair here will not move. Joint is essentially this. This will not move. So which means that although this body in planar state had 3 degrees of freedom, but because its one point is fixed, because if a rigid body, if any point is fixed, then it places constraint on all the points. This point is fixed means even this point also does not have freedom, because of, since this is fixed, right? This is fixed. Then restrictions are even here. This is also restricted because of this. So you see how it happens in a rigid body. Well, it happens for a rigid body. But if it were a deformable body, then there is no such condition. Like if any physics fixed, this still has some freedom that can still, it can take this some deformed shape. But in this case, it's not possible. Now, because of the fact that uh, this point has uh, cannot move, then it means that the XY coordinates of, I'll just call it some point P. I'll call that joint as point P of P is fixed, which means that no translation possible. So if say no translation is possible, then Deepak, what's left?
Yes.
So then what
Only
will be left?
rotation will be possible.
Yeah,
Only
so
rotation
only
will be possible.
yeah, so only rotation possible. Which makes it degree of freedom 1. So that's the reason we say that a hinge joint has just 1 DOF. Isn't it? So that was, yeah, I think I hope it's clear now. Yeah, because yeah, that's what was in the case of hinge joint. Now using this, we can move to other joints, and the same logic applies everywhere. So what we have is the next in this sequence is prismatic pair. Now in prismatic pair, as per the lecture notes, it's that you have a body here and there is another body, and it has some crevice, and the other body has something fixed here, something like a cuboid like structure. So there is some cuboid, and what he calls is as slider. Because of this slider, what happens is, and since they're all rectangular faces, this is body 1 and this is body 2, and body 1 is grounded, which means fixed. And this is, and I'm just taking some arbitrary shapes. So let x be a xy coordinate system be such that I'll just rotate it, because then it becomes some sort. Leave it. Let's let it on there. So what I'll do is I'll take xy coordinate system in a different way. This just to make some certain things understandable. So there's xy. Now the body 2 is able to move along this slot. It can move this direction, to and fro in this direction. And when I say reorient, and I say I bring it x like that and y like that, or I should have done here itself, because it's just I'm just making things complicated. Can it be rotated? No. Okay, what I'll do is I'll just redraw this figure. So say we have x and y, and we have this fixed here, and we have this body like this. This is body 1, this is body 2. There is slot and a slider, then this slider is fixed on body 1. Now I can remove this, erase this. And this, because of it has rectangular faces, so it can only allow the slot to move in this manner. This is grounded. Now you will say, okay, but in XY plane, the motion is like this. So you will say, okay, but it's able to move along X and Y directions, right? Isn't it what do you call, Deepak, like the translation is X and Y?
Yes, yes.
So how many degrees of freedom does this have?
It will be 1 degrees of freedom.
But you see, right? So why 1?
It is a prismatic joint, but I think it is a prismatic joint in one direction. It is a prismatic joint, link 1.
Yeah. Huh.
I'm just watching this figure.
Yeah, but why move along X and Y directions?
X and Y.
Then why it has 1
Prismatic.
degree of freedom?
But it is a prismatic joint, hence it can move in the rectilinear direction only, I think.
Yeah, it is rectilinear direction, but the thing is,
The
while it's motion, but during the motion, X and Y both are changing, right? while this point is
Yes, yes,
while
yes.
this body is moving from here to here, x and y are both changing. That means that it's able to undergo motion in both directions, x and y.
Yes, yes, yes. Yes. 2 degrees of freedom.
Then so it should ideally I mean it has then by this from the uh, say initial guess we can call it that it has 2 degrees of freedom, right? Since x and y coordinate systems can both change, coordinates can change during the motion. So, but what is stopping? I mean, so why we call it one DOF? So that is the, I believe that's just for discussion, like why.
Yes, yes, yes.
Yeah. So the answer
Like our
is
piston
yeah,
arrangement, this, yes, cylinder piston arrangement, this link 1 and link 2 are arranged, I think.
yeah, yes, 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 yeah.
Uh,
So the question,
that means
yeah. So
one link
that's
can be
the thing is, uh yeah.
piston arrangement, cylinder piston arrangement. Uh,
Mm-hmm.
one link can slide with respect to another link.
Exactly, that's true.
Here,
Yeah, the thing is, this is also a system. So, I mean, this is just an abstract form of system. What do you call that piston cylinder arrangement? Uh, yeah, it's just an abstract form. But the thing is, we are just wanting to understand why it's one DOF, not two, because we can clearly see that the motion can it's taking place along both x and y directions. Then why degrees of freedom is still one? So we are just trying to understand why is it so. What could
In rigid body, every point take only linear motion.
yeah, but still, right? We can clearly see that x and y directions are changing, x and y values. And translation is in both. Translation in both x and y. Then also then the DOF should be 2. But it isn't, right? But it isn't. Why? That is the question. Like this thing always props up, like the question why in such scenarios. Uh, so the what how we can approach, I mean, how we can explain the situation is, say when a body is moving along this direction, right? And say it started from this point here and then moved along further down. Say the body was a time when this slider what okay, why is it happening like this? Where is that? Okay, I'll just go. So at the beginning, what happened is the slider was here. I mean, in the sense that the body was and the slot was such that and this cuboid was here. I mean, the slider was here. And then this body moved upwards, and then this slider, I mean, the slider was still the same, it's just the slot was moving further like that. Then what happens is, one simple way to understand is with respect to, say, we consider this to be the initial displacement. We consider this to be initial displacement. Come on. And then it's just keeping on increasing. It's keeping on increasing from the slider. So what happens is, although the displacement looks like this displacement I'll call it measure using call S. So this is S, right? However, what we see is because of the virtue of the arrangement of this geometry, you can only move along this direction, and this makes an angle some alpha with respect to x-axis. So what happen is, and I'll just draw it nicely, I mean clearly, so that it appears x and y. When you look at the displacement along x-axis, like what is the projection of this on x-axis, then from trigonometry, this is equal to the base of this triangle. So this is a right angle triangle. This is a right angle triangle. So the base is such that it becomes s cos alpha. And the height of this triangle, or the altitude of this triangle, is s sine alpha. So which means that the displacement along x and y are not independent. Are not independent. Why? The reason is because by the virtue of the geometry, alpha is known. Alpha is already known. Alpha is known before, from the very placement of this, because we can clearly define alpha even in this case. How much the one edge of this slot makes with the x-axis. Alpha is known, which means and how they are related, their displacement, I'll call it displacement along x direction, is equal to s cos theta, s cos alpha, and displacement along y direction is s sine alpha. So alpha is known, which means that even if the body is being able to translate, right? It's translate in x and y direction. X and y. However, even we were able to see that, okay, body is translating in x and y direction. However, the only thing unknown is s. And if we have just one variable which is changing, so it implies 1 degree of freedom. I hope I'm able to make sense. Like, I think two of you responded, Deepak and Zanindra. So I hope I'm able to make sense here.
Yes, yes, yes. We got.
Yeah. So that is why we call it. So that is one way of approaching the problem. The other way of approaching this problem is, we know that mechanisms need only relative motion. We don't care about the absolute motion of all the particles. So which means that even if we had this coordinate system like this, and even if the entire body, like this entire mechanism was rotated, the entire body was rotated, sorry, the entire mechanism was rotated, it would not affect the working of mechanism. At least right now. Later we'll see that no, it affects, but right now, no, it does not affect. Which means that if we're able to rotate this entire body, I'll pick up a different color. If we're able to rotate this entire mechanism in clockwise direction, then what happens is we would be able to x and y, we would be able to orient the slider along x-axis. And likewise, the body, this fixed body would be like this. It would have something here. This is the fixed body, body one, and this is the body which can move. So what happens is now we can clearly see that the motion is only taking place along which direction? Just along x. Yeah, just along, exactly. Just along x direction, which means that now it's straight for our one off. So there are two ways of approaching. Yeah. So that was one approach, which seems to be much more tougher, and this is the easier approach. The only thing is one approach is the approach number one is more mathematically rigorous, and it gives us a very fundamental idea of what we mean by degree of freedom. So many a time degree of freedom is not very straightforward. It's just some the orientations that we are considering. So we make it simple for us to figure out. But in general, degree of freedom is never, it's not very straightforward. In this case, we saw that the degree of freedom is S. S is the degree of freedom, which is just one. I mean, one in number. And in this case, by rotating and using the other definition of mechanisms that, okay, the only motion which is allowed in which what we call to have a mechanism, we need relative motion. But when we rotate the entire mechanism, the relative motion does not change. If it was say moving like this with respect to this direction, say we fix this axis and this axis, it was making some angle theta. Even now, it's still making an angle theta, which means that we have not interfered with the relative motion. Till the time we do not interfere in relative motion, we can do whatever we want with the mechanism. We can take the entire mechanism, rotate, does not matter. We can move it from one place to another. It's just that the relative motion should not be affected. And we are able to clearly see that, okay, this is how we define, we are able to determine the degree of freedom for a prismatic, or force. In this example, it's prismatic, but for a general case, that's how we are able to do. So next, what we'll move is, we'll move to what we call as the screw pair. So in screw pair, what happens is we have two connections. We have a connection between, say, one body and the other body, which looks like a screw. So something like this. I don't know clearly how to make it, but that's how it should look from the side. And these are just the windings, the sharp windings. So what we, as we rotate it about the axis, about the central axis of this screw, then it is able to move into the body and say this is fixed. It's able to pass through the other rigid body. So, which means that providing one rotation, we are providing rotation, and then it's displacing, it's linearly translating. So which means there is some S displacement here. So what we say is, in this case also, the degree of freedom is such that one rotation is creating linear displacement. But you will say, okay, but there is a rotation involved, there is linear displacement. So there is a, we'll say that, okay, that's again one conflict again. So there is one R and one translation. So we should call that, okay, it should be 2 degrees of freedom. Should be 2 degrees of freedom. But it isn't. Why? So screw pair has how many degrees of freedom from the lecture note? It has one DOF, right? From as per the lectures. The answer is why? Because we are able to see two motion taking place, rotation and what you call translation. So how do you explain this situation? Why? Why is it?
Because rotational motion at initial stage.
What is the what is could you please repeat?
Because the rotational motion comes again in initial stage.
Okay, okay. And could you please, I mean, can you move further from here? Like, say we gave initial rotation, it was creating translation. But then we have this 2 degrees of freedom, right? Because and as we rotate, it's translating. So at any point, rotation and translation is going on at the same time until we are able to fully lock. I mean, fully reach the head of the screw. Say somewhere the head is will be here, right? Some head is here, and then it starts like this, right? Screw. So till we reach here, it will the both things will go simultaneously. But the answer is, but the question is why we do not have two DOF in this case, although it looks like.
We can define translation motion by rotational motion.
Exactly, yeah, that is the answer. That translation and rotation are related. So in this case, translation is it's a byproduct of rotation. So it's rotation which creates translation, and they are proportional. That is the that is the main thing here. Although rotation and translation is related, but that does not mean that okay, they are. I mean, that does not mean that they are independent. So we have to specify that they are proportional, and they're also directly proportional, which means that the more we rotate, as we rotate more, the translation also increases in a similar way. And then what happens is any particular, say, one level. I mean, I just want to say that if there is, say, 1 degree rotation, say rotation is some theta, and this is proportional to delta S. This is essentially this. And it so happens that delta S is equal to, and this is proportionality sign, some K into delta theta. And K is a constant. So which means that we have delta theta as the independent variable if we go by calculus, and delta S is the dependent variable. So which means only independent variables are considered to be degrees of freedom. So one rotation, I mean, its translation follows from the rotation because of, and they are directly proportional. Because of these reasons, the degree of freedom is just 1. Because the others, what we would have ideally guessed, is directly proportional to the rotation. And that's the reason we cannot call it as a degree of freedom, because it's dependent on something strongly. So that's why screw pair has just 1 degree of freedom. So that's how we explain this scenario. Now we come to, I think we'll be able to finish at least all the pairs today. And now let's talk about cylindrical pair. In cylindrical pair, what is happening is you have this body and this rigid body, and through which another rigid body passes, right? And this rigid body, this is body number 1 and this is body number 2. Say body number 1 is fixed, this is fixed or grounded, and this can move, and this can rotate as well as translate. This can translate and can rotate. However, it says that there is the organization says that there is no such screw-like arrangement inside. It's just a cylindrical inner face of the block as well, because of which this body can just slide through this what you call through this hole in the block, which means that displacement you can do as much displacement without rotation. I mean, if you just simply pull it out, say you're simply pulling out, this means that there won't be no rotation. Simply pulling out, this will create no rotation. So which means it's one purely translational. And then if you rotate it, you can, if we are just rotating at one place, you are not moving it like, so you can rotate without pulling. It will be one rotation. So you can rotate and without pulling, and you can pull out without rotating. And it so happens that one does not affect the other. You see, I'm just giving two extreme cases: pulling without rotation. You are just pulling, no rotation. And the other extreme end is you are rotating without moving from the place. You are just rotating at one place, which means that S is equal to 0. This S is equal to 0. There is no translation. So since 1R and 1T are not related in any way, which means now we can have 1R plus 2 1T. They can be added to give 2 degrees of freedom. So that is the thing with cylindrical pair. However, had this been another screw-like approach, then so say if it was threaded, if this cylinder this was threaded as well, and the block inside this that would also was been threaded, then how many degrees of freedom it would have? So this is threaded, and even the inner surface is threaded with, I mean, in an opposite sense. Like then how many degrees of freedom is possible? Can you please respond, any of you? Like how many degrees of freedom we would have then?
1 degree.
Uh, I cannot hear, like
1 degree of freedom.
isn't it? The reason again, it goes back to the previous discussion that the reason is the same, that it does not affect, like, I mean, one will affect the other again. So that was the reason here as well. Okay, so that was the thing. Okay, so now we'll move to we have just one pair here, spherical pair left. So we'll move to that. So we have spherical pair. So in this case, you have one rigid body or link here with some hemispherical opening, and there is another hemispherical body here, which has at least one point contact. So at least there is one point contact, because if there is no point contact, which means it's separated, which means they are not connected. They are just two rigid bodies. So we want it to be in contact. So there is at one point contact here. Then only we can say that they are connected. Otherwise, it does not make sense to talk about it. Right? So what we'll do is just a minute. Yeah. So which means that this and this is grounded. This is grounded. Now grounded means this block here will not move. So will not move implies that what all is happening here? Which means that, and we are talking about space. Now it's a spatial mechanism or spatial kinematic pair that we are talking about, which means that X, Y, and Z are all fixed. So for this body also, the other body, this is body 1, this is body 2. For body 2, at least one point which is in contact with the fixed body, X, Y, and Z coordinates are all fixed, which means that what we have lost because of X, Y, Z being fixed. So a rigid body in 3D has 3 translations plus 3 rotations. So what all we have lost by fixing it?
3 translations.
What we have lost?
3 translations.
Exactly. So 3T is lost. So we are left with 3R only. Now you can rotate about x-axis. You can rotate about y-axis. You can rotate about z-axis. About x-axis, you can just take this. You can bring this part, align along x direction and rotate it, and do the same for x and. Because of which a spherical pair has 3 degrees of freedom. So that's the reason, yes, spherical pair has like that. Right. So what we'll do now is let's. I think time is to determine degree of a system, because since we have lack of time today. So what we'll do is. And we'll continue our discussions sometime. I mean, any doubts we'll discuss in the next tutorial session as well. So I'll just write down the formula. Planar mechanisms, right? So for planar mechanisms, if you have number of links, so I'm just trying to draw again some abstract. So links, joints, say something like this. So if the number of links is equal to NL, number of joints. So joints are like, these are joints, this is a joint. So 1, 2, 3, and there is this prism joint. So, right, joints is equal to, this one called has something like, again, some fixed thing. So Nj and the degree of freedom of each joint is of ith joint is equal to Fi. So in this case, this is I is equal to 1, this is I is equal to 2, I is equal to 3, I is equal to 4, I is equal to 5. So for I joint is Fi, then degree of freedom of planar mechanisms is equal to 3 into NL minus 1. In any such mechanism, ground is considered is what you call always numbered 1. So always counting starts with the ground. So ground is 1. Then this is body. This is link number 2. 3, 4, 5. And this ground is just the part of same ground, so we don't need to number it again. So ground is so that's the reason we subtract 1 always. So 1 indicates that we are subtracting ground from here. You'll ask, but why is why do it is why cannot we just take non-ground? But yeah, that is the convention which is being used. So NL minus 1. So number of links including ground. I'll call it. Then minus the number of degrees of freedom lost because of the joints, and then plus number of degrees of freedom just because of the joints. So this is the thing. And for this case, let's determine the value. Here, the number of 1, then this first link, second link, third link, fourth, fifth. So we have 5 links. And how many joints we have? Joint number 1, which is a hinge joint. And then we have hinge joint. So 2 hinge joint and hinge joint. So we have 4 hinge joint plus 1 what we call as the prism joint. So we have number of joints is 5, right? And for hinge joint, every hinge joint has 1 degree of freedom and every prism has 1 degree of freedom. Because of which summation of Fi from I is equal to 1 to number of joints 5 is equal to 1 plus 1 plus 1 plus 1 plus 1. It's like 5 times. So it's 5. So now number of degrees of freedom for the mechanism is 3 into 5 minus 1 minus 3 into number of joints, which is 5, then plus 5. So this will be equal to 3 into 4 minus, which is 12, minus 15 plus 5, which is equal to minus 3 plus 5, which is 2. Isn't it? So it's like 70 minus 3. So we have 2 degrees of freedom for the entire mechanism. Now here the problem lies is it's not very clear like what degrees of freedom are we talking about now. So there is where this it's not always possible to visualize the degrees of freedom in a very with a very precise with a very precise geometrical meaning. So even in that case, we have to construct it will be in such a space that the motion of one will be restricting the other, such that eventually we are only able to change 2 such parameters. So that's another thing, and that those 2 parameters can be something which we cannot imagine just by looking at the figure. Right. So that was for this, and one is for the say degrees of freedom for spatial mechanisms. So degree of freedom of spatial. In that case, number of links is L, number of joints is Nj, degrees of freedom of ith joint is equal to ith joint is equal to Fi. So degrees of freedom for a spatial mechanism F is equal to 6 into NL minus 1 minus 6 into lost because of joints plus summation of as T1 to NJ Fi. And using similar arguments, we can determine the degree of freedom for such problems as well. Now, before that, what is that? A mechanism must have at least one DOF. If there is not even one DOF, that means that it's useless constructing such a complex mechanism, because there is no degree of freedom, which means we cannot use it to do any purpose. Second thing is, a structure has zero DOF. So say a dam or a bridge, those are like, they all have 0 degree of freedom. Even a solid body kept on a plane, on just say you have fixed one body somewhere. Say a tower has 0 degree of freedom. Why? Because you cannot move it. I mean, it's fixed at one place. You cannot rotate. You cannot do anything. Although it's such a connected network of uh, links, but you cannot. It does not have any degree of freedom. So those mechanisms, I mean, those connections of, I mean, interconnected set of rigid bodies is called a structure. And third point, which is very important, is that an over-constrained system has negative degree of freedom. In that case, we cannot use these formulas, because these formulas assume that the constraints, so to speak, are independent, which will, I hope the professor teaches later. But for an over constrained system, you cannot find degrees of freedom using these formulas. These formulas are also meant for only for some special types of mechanisms, but not valid always. Right. So I think that was it. What I'll do is I'll just share my screen and then I'll just present you I mean, just for a simple demonstration. Let me share the screen, my laptop, and I just want to show you just for motivating purposes. So I have been learning this software. I mean, still learning, just it has not been very lot of days. So you can excuse me for not being good right now. I'm just trying to learn. So there is one software that I was talking about. It's called as a Coppelia simulator. It's meant for doing robotic simulations. We can code things up and then run it and see how it behaves. So this is just one tutorial, which I have not coded anything, to be honest, nothing. I am also just amazed at the visualization. So this is how it does, you see. So this is a robot which is meant to pick up glasses, fill water into other glasses, and likewise the other robot will do the same. It's just to motivate. So you see, so the path that this robotic end effector, which is the tip of the robot, takes, is what is called as the motion planning. And motion planning is very important to determine the work of any robot.
So
That is, yeah. Could you please?
yeah, actually, are you sharing screen?
Yeah, it's not visible, huh?
It's not visible.
Okay. I think I spoke so much. Okay. Okay, I'll start from the beginning.
Now it's
Okay, yeah.
Thank you.
So this is a software called Coppelia Simulator. I'm still learning, like I have just begun learning, so I have zero expertise. But we hope that as we move along the course, we'll try to figure some things out from this software. So this is essentially a software where we can implement algorithms with regard to how the robot should move. So here, this is a tutorial, just a tutorial from the software, which was shipped along with the software. So this is how you see. So this end effector, which is the tip. So there are two types of effector. One is called tooling, and here this is a grasp. It grasps. It has this gripper. Sorry, it has this gripper, which grips some object, does something with it, and then returns back to the position. And the path that you see, these yellow and purple lines. So this is the trajectory of the end effector. So the goal is always that the degrees of freedom for the entire robot has to be such that the end effector is able to take this path, because following this path, it can be made to serve some function. Like in this case, it's like pouring glass or liquid from one glass to another, then just arranging the glasses in some vertical or in some some tower-like format, or just stacking one over the other. So that is essentially the goal of. So we will, like, as we move along, we will try to, if possible, to try to understand this software just as a, we'll do it simultaneously, learn whatever was taught about in the corresponding week, and also try to figure out something of this software, and then learn if we can implement such algorithms in this, and if we can, then how it should be done. So that is something. I know we don't have much time in this course, so we'll try to get at least something done. Yeah, so I think that was just, this is just for motivational purpose, so that, yeah, we have some interest in pursuing this course and work together. I'll share the links to this software. It's called Coppelia Simulator, and then we'll try to figure things out if possible. And I also share one book that I had mentioned at the very beginning called Modern Robotics. So we'll also do that book as a side reading, because the professor has not clearly mentioned which book we are going to follow. So I think his notes are self-sufficient, but for practical robotics, we always need to move forward, in the sense that we have to. Uh, it always involves solving things using some software, either some software, or we code things in MATLAB. And there are other platforms called robotics operating system, which I think some of you may be familiar. It's ROS. To be honest, I don't know much anything about ROS. I only know about the overview, what it does, not the finer details. So yeah, I think that is what I had to talk about today. So yeah, any of you has anything to say, like anything to add?
Sir, tell me about yourself.
Okay.
Uh,
Yes,
yeah,
you have explained very nicely the concept of degrees of freedom.
yeah, we are
We learned
learning
many things,
together, I would call.
basic fundamental.
Yeah, yeah.
Thank you so much for your valuable
Sure, sure.
insights
So they were
regarding
like,
degrees of
we are
freedom. Thank you so much.
usually these fundamentals are some things where we stick, I mean, get stuck. So I think we
Right,
spend
right.
disproportionate amount of time, if I can call like that, on this. But still, I think it may be worthful to all of us, I believe.
Definitely, it will be helpful us. Definitely.
Yeah, yeah. Yeah.
Thank you so much.
Sure, sure. Yeah, no, Deepak, yes. So if there is not anything to discuss today, then I think we can close the session. We are already uh, beyond time. So yeah. So I'll just stop recording, and